These are your notes for section 8.4, radical notation for the nth roots. Mostly review today. There's a couple new concepts and a reiteration about when we use specific roots. Overall, I think this will be a pretty easy lesson for you. There's a journal choice for you. Basically, what we're going to do is we're going to be rewriting radicals by applying the root of a power theorem and the root of a product theorem, and we're just going to look at the properties of powers when dealing with radicals, because we know now that a radical is just a special power, a rational one. Okay, so what does a fractional exponent do, or a rational exponent? What does it do? And we talked about this in the last chapter. If you remember, the top is the exponent and the bottom is root. So x to the 1/2 we can rewrite as the square root of x. X to the 1/3 we can rewrite as the cube root of x. X to the 2/3 we can rewrite as the cube root of x squared, because the top is the exponent, the bottom is the root. And likewise, we can rewrite x to the 3/2 as the square root of x to the 3rd. This should be all review. This is what we did last chapter. Okay. Basically, the definition of an nth root, because we talked about rational exponents before we looked at roots, which is a little odd in some people's opinion. But basically, the definition is when x is non-negative. So we're going to say that the number underneath here has to be positive, and n has to be greater than or equal to 2. Then, and only then, can you write this root as a rational exponent. So basically, we went this direction last chapter. Now we're going this direction. They only want us to go this direction if x is non-negative. Okay, so let's solve for x here. Well, here's the root. We are going to rewrite it as an exponent. How would I rewrite it? I'd put it to the 1/7 power, and I now know that if the bases are the same, that was a horrible 8. If the bases are the same, then the exponents have to be equal to keep this equal sign's value. So x in this case will have to be 1/7. That should make sense. Okay, let's look at a couple more things. Don't be mean. Let's talk about averages. If I asked you to find the mean, we're looking for a representation of a data set, a group of numbers. You guys, when I say how do you find the mean, probably are like easy, and you're thinking of what is called the arithmetic mean, which should remind you of the arithmetic sequence, where you add the same number over and over and over again. Okay? You take the number of terms, you add them together, and divide by that number of terms. You've done this since elementary school. You have not used the geometric mean, I'm pretty confident, up to this point. And the geometric mean is very, very similar. You use it for the same purpose. It gives you a good representation of what your data set represents. And what you do in this case is you're going to multiply all the numbers together instead of add, and then you're going to take that nth root. We use both types of means in statistics, and when I took my statistics class last year, I asked, what is the difference? The main difference is geometric is better. Geometric is better because it doesn't take into effect outliers as much. So if you have a data set where all the numbers are pretty much in this range from, like, let's say 10 to 20, but then you had one up here at 40. Okay, when you do the arithmetic mean, it has a larger effect than if you take the geometric mean. This one won't affect it as much because maybe that was a mistake. So usually, as a rule, geometric mean is more accurate. However, we barely ever use it in statistics. This is not used very commonly. The reason being because when you multiply, if you have a huge data set, let's say you have 100 terms, when you multiply 100 numbers together, it gets humongous very, very quickly. And a lot of our devices, such as calculators, computers, they can handle it, but we don't always have a computer handy. There are limitations to our calculators, so it's not always convenient to use the geometric mean unless you had a computer handy. So they don't use it as much because when they're dealing with larger data sets, statisticians generally do, it gets too big too quick before they can take that root. Okay, so that's a little background info on geometric mean. Here is an example. The following chart shows the population for 8 1 square mile regions in the United States. I really think that this chart is pretty cool. 1 square mile. So we're what, 1 mile by 1 mile. We're talking about little squares. I like to think of maybe Jerseyville here. If you take a sample right out of the middle of Jerseyville, you're going to get a pretty large number by how many people live in that square mile. You go out to, I don't know, the rural edges of Fielden or Grafton, and you get a way smaller number of how many people live in that square mile. Okay, so this should make sense. They took a sample. This is obviously being taken in a city. Maybe there's an apartment complex or anything else. Maybe a rural town and out into the country. Okay, they want to use a geometric mean to compute an average. They want an average here. So what we're going to do, and I don't know if your calculators can handle this or not, is you're going to take 47 times 68 times 159 times 2215 times ... times 45,312. As you're typing this into your calculator, as I'm doing so right now, and I hope you are also, it is going to get really large. That's why I'm not going to hit equal until the very end. And I don't know if it's going to say error or not. I don't remember. That's why I'm actually doing this with you. I'm hoping I'm not going to make any typos. Yeah, it's going to say, it's going to have that scientific notation with the E on it. Keep that value in your calculator. Do not touch anything. How many data pieces did I multiply together? Okay, what was the sample size here? Well, I multiplied those all into my calculator. I got this number. Mine says e to the 25. Okay, it actually says 5.6 and some change. Keep that in your calculator. You're going to hit the caret key. To what power? Well, I need to take it to a root. What root? I'm going to take it the 8th root of it. Okay, I'm taking the 8th root of all this. There is another way I could write that. I could put caret parenthesis to the 1/8 power. And I should get a very manageable number of 1656.4. I'm not going to say 0.4 because I don't have a 0.4 person, but sometimes when they're talking about density, they don't mind it. It's up to you or what the directions say. So they're saying based on this data, then a good average would be 1656 people. Okay, that was the geometric. I know you could all take an arithmetic mean of that if you wanted to. Just add them up, divide by 8. Very similar. Most kids don't have a hard time with it. Once you talk about the sequences, the difference in arithmetic and geometric sequence, this makes perfect sense to you. Okay. The biggest thing here that we need to remember is that radicals are just exponents. Because all radicals are exponents, all the exponent and power rules do apply. So basically, I prefer to change my radicals to exponents because I am more efficient with exponents. But you can just remember the rules. So first thing you do is you're going to take your radical and you're going to change it to a rational exponent whenever you get the opportunity, and that is the root of a power theorem. And since we already went this direction last chapter, this should make perfect sense going this way. So here's an example. Suppose that x is greater than 0, because they had to say that in order to take it from a radical to a rational exponent. Use the root of a power theorem to write this in two different ways. Okay, so that's going to be x to the 18th over 6. That's one way we can write it. That is the exponent. That is the root. I can write that as x 18 divided by 6 is 3. There's two different ways I can write it. I could write it as x to the 6 over 2. I could write it as x to the 9 over 3. The possibilities are endless. It is super fun. Okay, they want to show that this does not equal that when x equals -2. Well, the best way for me to do that would be to actually compute both ways. The 6th root of -2 to the 18th power. Okay, let's take -2 to the 18th power in our calculators. And I get the 6th root of a positive value. -2 to the 8th power is going to be positive. 262,144. I then take the 6th root, or I could take it to the 1/6 power, and I get 8. Now, let's do this. Negative 2 to the third power. Negative 2 to the third power, an odd number of negatives, is going to give me negative 8. See what happens here. This can simplify, which is 2 evens, can simplify to something that is odd, which is why we have to make that stipulation that this has to be positive, because you cannot simplify a rational exponent and drop the value of those negatives, okay? So this is a perfect example as to why you have to make that stipulation that it has to be non-negative. Okay, I love this. These problems may have showed up on a math league. They're not hard, okay, but they look super duper hard. And I hate how my math script makes the parentheses bigger and bigger, because it's not that they don't have to get bigger like that. It's kind of stupid, actually. But what does this mean? Well, this means the square root of the square root of the square root of the square root of 10. Okay? This is very overwhelming. This is not as bad, because when I change this, the square root of 10 to 10 and 1/2 to the 1/2 to the 1/2 to the 1/2, what we have here is a power to a power to a power. When we have power to a power, if you remember, x squared, to the fourth power is x to the 8th. We multiply our exponents when we have power to a power. I'm going to multiply all these 1/2s, and I'm going to get 10 still. Don't change that base, but multiply 1/2 times 1/2 times 1/2 times 1/2, and we get 1/16. Okay? So you could just write the 16th root of 10. Those are equivalent statements. It's kind of interesting and fun, I think. Okay, this is a lot of words. Basically what this is saying, again, is when you have this symbol, just like when you had this symbol, we're not talking about all of them. We are only talking about the positive ones, okay? We assume positive. If they are wanting you to give a negative root, they will stipulate that by putting a negative in front of it. Now, on your quiz or your homework, they might ask you for all of the fourth roots of 81. If they ask for all the fourth roots of 81, you should realize, well, there should be 4 of them. Okay? When you take it, if I just write the fourth root of 81, though, that is not asking for all of them. That is only asking for the positive one. The fourth root of 81 is 3. But if I am writing as for all the fourth roots, you would have to write 3, negative 3, 3i, and negative 3i, because that's asking for all of the things that will make x to the fourth equal 81. If it's written this way, they're asking for all of them. If they're writing with a radical notation or rational exponent, excuse me, not x, yeah, I guess that's fine. But 81 to the 1/4, I should put. They're only asking for the positive. Positive, all of them. Or they could write the words all of them. And by all of them, I mean complex, negative, all the above. Okay? So here's an example. If they ask you to evaluate the fourth root of 2401, what are they asking for? They are only asking for the positive value. And I would tell you that the answer is just what my calculator would, 7. If they ask to find all the fourth roots of 2401, we're not going to use complex number mode. We're going to use this by common sense. They're asking x to the fourth equals 2401. What will make that true? Well, 7 makes it true. We already established that. But guess what? Negative 7 will also work. There are 2 others, 7i and negative 7i. Because when I take I to the fourth power, that gives me a positive 1. Oops, I forgot my I here. Okay? So if they're asking for all of them, you need to consider the imaginaries as well. Okay, we are going to evaluate these without using a calculator, and some of them you might still. They basically just want you to take 64 to the 1/6, and like I said, I do know that that is 2. Some of you might be able to guess or figure it out. If you have to break out a calculator a little bit, that's fine. They really just want you to practice going back and forth from radicals to exponents. Square root of 169 is 13. We do know that one. Cube root of 512. 512 to the 1/3. I don't even know, really. 512. I should probably. Yeah, it's 8. I didn't know it. So if you had to type some of these in your calculator, I always say if they wanted you to not use your calculator, they should have done a little bit more mental math problems. Be careful here. This is the 4th root of 16 plus 81, which is 16 plus 81 parentheses to the 1/4. You have to add that first, guys. You can't just take the 4th root of 16 and the 4th root of 81. That is illegal. So 16 plus 81 is 97 to the 1/4. Basically, they want you to estimate the nearest hundredth. They want you to go ahead and type these into your calculator. Okay? Find all the complex roots. That is asking you, again, for that x to the 4th equals 65, 61. You should have 4 answers. Some of them should be imaginary. Which one would be equal to this? They're talking about the positive value only. We'll talk about some of these tomorrow in class. Consider the statement. Which values of m is the statement true? What was that stipulation you had to make about m? Okay. And same thing here with the counter example. Try to plug in some negatives. See what happens. What are the possible values of m for the radical expression, the mth root of n? What could I plug in for m here? Is there a such thing as a negative root? No. So m has to be greater than or equal to, there's not really even a first root, there's a square root. So 2. And how about n? What can you plug in there? N has to be greater than or equal to 0. Okay. Like I said, we'll talk about a lot of that tomorrow, and that's really all I have today. The biggest deal is to really just be careful about when you're considering the positive ones versus the negative ones, and to realize that you have to make that stipulation that underneath that radical needs to be a positive value. Okay? Where's that at? Right there. Okay. Thanks, guys.